Hello guys, good evening.
Good evening, sir.
Yeah, so I think last class we started with Grignard Reagent, no?
Yes, sir.
And we have seen few reactions of this. I think few examples of nucleophilic addition reaction we have done in the last. Correct? So,
Yes, sir.
so the reaction of Grignard reagent with carbonyl compound, it gives what? It gives nucleophilic addition reaction. Okay. The R group of Grignard reagent behaves as a nucleophile and attacks onto the carbonyl carbon. Okay. So we'll see some more examples, 2-3 more examples in this, and then we'll move on. Okay. Could you tell me the product in this reaction? PHMgBr reacts with carbon dioxide. A and then with H plus H2O. B. What is A and B here? Okay, so the first product is what? You see this CO2 is this compound. We have C double bond O into this. And this pH minus behaves as a nucleophile here. It attacks onto this carbon and this pi electron goes up onto this oxygen. So A for this would be, we have pH C double bond O, O minus and Mg Br plus, which on reaction with H plus H2O, it converts into benzoic acid plus MgOH Br. This is the product we get. Okay, benzoic acid. Okay, now you see when you have this nucleophilic addition reaction, then obviously we have to check the tendency for this R minus, how this R minus can easily attack onto this carbonyl carbon. Okay, if this step is easy, it means the rate of reaction is more. Correct? So if they ask you to compare the rate of this kind of reaction, compare the rate of reaction, nucleophilic addition reaction. Okay, so this rate is what? This rate is inversely proportional to the steric crowding around the carbonyl carbon. I'm just writing it down, crowding around the carbonyl carbon. If it is more crowding, SN2 attack will be difficult and hence the rate will be low. And it is also directly proportional to the positive charge density on the carbonyl carbon. Positive charge density on the carbonyl carbon. Correct? This is the relation we have for the rate. Copy this down, I'll go to the next slide. So either you have to check the positive charge density or crowding or both in any question. But these are the two factors you need to consider. Look at this question.
So what do you mean by the positive charge density?
I'll tell you. Look at this question first. We'll explain by this question. Suppose we have HC double bond OH. And then we have CH3, C double bond OH. And then we have CH3, C double bond OCH3. You need to apply the concept of GOC over here. See, this carbon has delta positive charge. Yes or no? If you talk about crowding, where we have maximum crowding?
The third one.
Last one, because of methyl group, right? Maximum crowding. Hence, least will be the rate of reaction. That is the one thing.
So
And
even,
second, yes.
so even positive charge will be least because
Least, yeah, that's what I wanted to tell. Because this delta positive charge, if this delta positive charge density is maximum, then R minus will be easily attracted towards the carbonyl carbon, right? R minus of RMGX. But since CH3 shows plus I, right? So this will reduce the positive charge density maximum. So crowding plus positive charge density leads to the order of the reaction should be this, the rate of the reaction should be this. Yes or no? Understood this?
Yes, sir.
Right? Okay.
So the positive charge density is density is like more dominating factor here, right?
No, it's not like that. You see, both the factors are giving the same order here. Right?
Okay, yeah.
So they won't give you, the question in which you have a contradiction. They won't give you like that, because then it will be difficult to, compare, right? So they'll give you either with respect to this or with respect to crowding. Both also, if you consider, we are getting the same order.
Yes, okay.
Okay, and if they give you some kind of contradiction in the question, then the option will be like that, so that you can easily eliminate options and get the answer. Okay, so you don't have to worry about that contradiction. So if the Hughes minus I group attached to the carbonyl carbons, that would increase the positive charge density and hence the rate of the reaction. Advik. Okay. Yes, Advik, tell me what happened. Any doubt? Hughes minus I group increases the positive charge density and hence the rate of the reaction. Okay. And here we have CS3. Tell me the order here.
So should we text it?
So
Should
2
what?
and 3.
Yes, I didn't get you. Come again.
So the second one, first one, and then the third one.
Second one is the most, right? Reason?
So NO2 is electron withdrawing group.
Minus M. What effect we have here?
So you have
Plus
plus
I.
H.
Plus I.
Plus H.
Plus
And there is no such effect, right? So plus H reduces the positive charge density, minus M increases the positive charge density. So order is, this is 1, this is 2, and this is 3, the rate of the reaction. So basically, when you see the question, you will understand that what factor you need to think about. Okay. Here, what factor we'd apply?
Steric hindrance.
First one has more steric.
So this one is more, shows more rate of reaction. Easy? Okay, so this is nucleophilic addition reaction. The another type, we have the third type of reaction that Grignard reagent shows, that is nucleophilic addition elimination reaction. Okay, kind of nucleophilic only, nucleophilic addition reaction only, but there is a good leaving group attached to the carbonyl carbon. In that case, it is possible. Okay, I'll show you how. The third type you write down, it is nucleophilic addition elimination reaction. Means addition plus any elimination takes place in this reaction. Okay. So nucleophilic addition elimination reaction, write down. It is possible when a good leaving group attached to a carbonyl carbon. Okay, for example, you see, suppose we have carbonyl chloride, RC double bond O Cl, carbonyl chloride, and this reacts with RMgCl. Okay, so the product of this reaction would be, suppose it is R1, and the product would be RC double bond O R1. This is the product we get. Okay, plus MgCl2. Okay, so how do we get this product? So first of all, you see what happens. In the first step, the R minus here behaves as a nucleophile, correct? This will attack onto this carbon atom, and when this attacks over here, the same thing, it goes up. Correct. So the product here is, we get RCO minus R1 and Cl. So you see this sp2 hybridized carbon now converts into sp3. Okay. Next step was what happens here. In the next step, so this is nucleophilic addition. If you see, it is similar to the previous type that we have discussed, nucleophilic addition. In the next step, what happens when this lone pair of electron comes back to form a pi bond here, this goes out as a leaving group. Okay, so this one is what? This one is elimination reaction in the second step. So the product is RC double bond O R1, and this Cl minus that comes out takes this MgCl, forms MgCl2. Okay. You can write Mg plus Cl also over here, Ruchir, just to neutralize this. But this is what, it is not, it won't, form a bond with MgCl. MgCl will be present here around this, right? Because positive negative attracts, but the bond won't form between oxygen and magnesium. Okay, it will be free in the solution. So when it comes back, this leaving group goes out. Okay, you can ask me, so why this R minus attacks onto this carbon atom? Why not at the same time the Cl minus goes out? Okay, that you can ask. But the thing is what, here when this Cl minus goes out, for this thing you need to break this sigma bond, which is a stronger bond, correct? So for this pi bond, it is easier to shift onto this oxygen because it is a weaker bond, pi bond, plus oxygen is a good electronegative element also. Okay, Cannizzaro reaction is a bit different, Ruchir. It is not same here. It is an oxidation reduction reaction. Okay, so that also will see.
That also like the double bond goes like that and then H comes.
Carbonyl compound reaction is like this only. Pi bond shift onto this oxygen. But Cannizzaro, this kind of shifting takes place in all reactions of carbonyl compound. But Cannizzaro is one compound get oxidized, other one get reduced. Okay, we'll discuss that later. Okay.
Okay.
So a little bit different pattern of reaction we have over there. So you can ask me, why not this, when this attacks onto this, why not Cl goes out? The reason is what? For this Cl to go out, you have to break this sigma bond, which is stronger. Here, pi bond, a weaker bond, oxygen, more electronegative, can easily attract this pair of electron towards this side. And that's how it happens. Now, when this comes back, so this is a good leaving group, right? So it can easily go out in comparison to R and R dash, and you'll get this. So point is RCOCl, it is acyl chloride, correct? Acyl chloride gives you ketone in this reaction. Okay, so this is what the product in this reaction we have. But again, I'm telling you one thing here, that it is not like you always get ketone in this reaction. It depends how many moles of RMGX you are using. Could you tell me what happens if we use excess of RMGX in this?
So we'll get an alcohol.
Yes, because when excess of alcohol you have, so further that RMGX reacts with ketone and converts into 3-degree alcohol. Are you getting it? Tertiary alcohol.
Yes.
Yes.
Sir.
Yeah,
Okay.
that's
So next, the same thing you write down. If RMGX presence in excess. Present in excess, then what happens? Okay, so first of all, the reaction is RC double bond O Cl reacts with R1 MgCl excess, right? So the first product I'll write down here, RC double bond O R1. You should also know how do we write down the product directly. Okay, that is also important to understand. But since RMGX is in excess here, so this converts into, can I write down the product directly here? This converts into RCO minus R1 first, and then this is allowed to react with H plus H2O. This is understood in this reaction, and hence it converts into ROH R1 plus, we get MgOH Cl. Clear, no? So excess of RMGX with acyl halide eventually converts this into alcohol. So all these reactions are given in alcohol chapter. Okay. Done this one? Can I move on?
Wait, sir, 1 second.
Acha, R2 I have written here. It's not R2, it's R1 only. Any alkyl group, R1, R2. You can take here R2, you will get R2 over here. Any alkyl group. Okay. Write down the product in this reaction. CH3, C double bond O, OCH3 on reaction with CH3 MgCl excess, and the second step we use H plus H2. Write down the product in this reaction. If you take two Grignard reagent, then the required products can be separated out. Two different Grignard reagent you are talking about. Yes, so the product could be an chiral compound. See, it's not like, just a second guys, let me go back first, then you can try this. See, first of all, one thing you have to take care of here. You won't get ketone and this mixture you won't get. Okay, if you are taking excess of it, then all these ketone converts into alcohol. So eventually you get alcohol only. You won't get the two compound. This alcohol may be chiral, may not be chiral, depending upon these R group that you are taking in different steps. So mixture of product, Advik, you won't get. Yes. Which half you are talking about, Advik? See, first of all, I don't know what two compounds you are taking. I am telling you that you won't get two compounds. You'll get tertiary alcohol. That is it. If it is excess, because it is a stepwise. Okay, it's not like in one step you are getting two possible mechanism. It is a stepwise reaction. Okay, first you get ketone and that converts into alcohol. Yes, when two different Grignard reagent you take, this would be chiral then. Yes, this would be chiral then, and it has two form actually. In that case, it will be chiral, and it has two form, that is R and S. That too you can obviously it is not discussion of this chapter. That too you can separate by different methods, two different compounds. So answer in that case would be two isomers of the same alcohol we get.
Sir, but that carbon won't be chiral, right?
This one is not chiral. I'm talking about when these three alkyl group is different. Then it
Sir, but it can't be different because anyway the R1 will again attack on this if we use excess of it.
No. You see, it's just a case I am taking here.
Okay.
In that case, suppose you take 1 mole of R1 MgCl, and then in the second step you are taking R2 MgCl. Then it would be.
Yes, sir.
Got it?
Yes, sir.
Yeah. So there, if you take excess of this, then you won't get chiral carbon. But it is like this with this gives A, then again with R2 MgCl gives B, and then H plus H2O gives water. In that case, the final product, the final alcohol would be carbon. Okay, write down the product in this. Is it this one? CH3, COH, and with this carbon atom, we have the 2 alkyl group of Grignard reagent. Is it? Tertiary alcohol we get.
Yes, sir.
Yes, sir.
If it is not excess, then the answer
Yes,
would
sir.
be a ketone, and that would be CH3COCH3. Okay, try this one. You should know what all good leaving group. I have already discussed this in reaction mechanism. OCH3. OR is a good leaving group. Halogen atoms, chlorine, bromine, iodine, good leaving group, right? OPH, also a good leaving group. Okay. OCO double bond CH3, good leaving group. Okay, so this idea you should have. All these are good leaving group. I've discussed this already in reaction mechanism. Okay.
So if it's not a good leaving group, what will happen?
Then this reaction is not nucleophilic addition elimination is not possible. One possibility I'll discuss now, that if it is not a good leaving group given in the question, then the reaction and how they frame that question I'll tell you now. Okay, just give me 2 minutes.
Yes,
Okay.
sir.
Okay, try this one first. Double bond O, and the reaction of this with CH3 MgCl excess, and the second one is D plus H2O. D plus H2. Okay. So the product here is this. We have two methyl group present over here. And here it would be OD and OD, is it? Because H plus comes from, okay, H plus comes from this, it's not from water, but it is from this acid H plus, okay? How it happens, you see, this R minus attacks onto this carbon atom, carbonyl carbon, right? And this bond pair comes over here, right? The ring open up, right? So we get what? We get this. Sorry, just a second. Just a second. This attacks onto this, and this pi electrons shift onto this oxygen. And then we get this one, O minus. Correct. Next step, when this comes down to make a pi bond, this comes here and the bond dissociates. So it converts into double bond O, and we have this ring with oxygen minus, and this is plus. Okay. Next step, again CH3 MgCl. This is CH3 now. And this will be CH3 this side. So next step, what happens? H plus H2O, 2 moles of this will use. H plus H2O protonates this oxygen and this oxygen also. That would be, you will get double bond OH. See, we are using D plus D2O, not H plus H2O. So we are using D plus D2, H2O here. So here we get D, and one side we have this OD, and this is CH3 with positive charge on this oxygen.
Sir, but we're using excess of Grignard, right? So won't
Yes,
the
sir.
Grignard react before the protonation?
Yes, sir. We're not gonna tell.
No. Actually, when you have this O minus, then MgCl, see, MgCl won't attach with oxygen. No, it will be O negative.
No, yes, sir, but the CH3 will attack on the carbon which has the oxygen, right?
This one you're talking about, or this one?
No,
This
sir.
case?
There's one carbon bonded to O minus, right? Like the double bond O.
This one, this one, this one.
Yes, sir. So won't the CH3 minus attack there again?
Here you're talking about?
Yes, sir. And again, the pi bond will go to
one
oxygen.
mole also. That's what I'm thinking. Why I'm not getting here one more CH3? Correct. You are saying correct. I'll just finish this just a second. That's why I was thinking why I was not getting this. Okay. So next step, what happens? The same thing. Reaction of ketone with RMGX. Okay. So this won't be here. The next step we get is this. Then only we get 2 CH3 here. So next step is what? CH3 MgCl. This again attacks onto this, and we get here O negative, then CH3, CH3, and this ring which opens up will be like this only, O minus, and then it attacks with excess of H2O, H plus. 2 moles of this we use D plus H2O. This D plus comes over here, this D plus comes over here, and it converts into this molecule.
So how does the D plus attack on both
Just
places?
a second, tell me.
So how does it attack at both places?
We have this is solution, no. So we have excess of it.
Oh, perfect.
So this will protonate this oxygen also and this oxygen also.
I think the final answer is missing a carbon.
Yes.
So the final answer has one less carbon, like the yellow structure.
How many carbon atom we have here? 1, 2, 3, 4, 5. So we have 1, 2, 3, 4. One more carbon atom will be there. I'll draw it again. What happened in this? So this is the mechanism. Next, what happens? We have 1, 2, 3, 4, 5 carbon atom. Correct. So we have OD here. 1, 2, 3, 4, 5 carbon atom, and here also we get OD. Correct. Yes, we get OD here, and here we have 2 methyl group. Is it right now?
Yes.
1, 2, 3, 4, 5. At 5th carbon we have 2 methyl group. So 1, 2, 3, 4, 5. Yeah. So 1, 2, 3, 4, 5. Yeah. At 5th carbon we have 2 methyl group with OD attached to it. Correct. So this kind of question you may get. Correct. If you have H plus H2O, then you will get diols. Okay, diols. Same kind of mechanism. Now, suppose what happens if the leaving group is not given there. Like suppose in this example, RC double bond O, OH. Correct. Since OH is not a good leaving group, then they'll frame the question like this. In the first step, they'll ask you to react with TSCl. A you'll get, and then you will be asked to react with RMGX with H plus H2O, excess of it. Now, could you tell me what is the use of this tosyl chloride?
So nucleophilic substitution.
So what it does, why we use TSCl there?
So the Cl and OH will be replaced.
Cl and
OH.
Cl and H.
It makes OH a leaving group.
Yes, OH is a poor leaving group. Correct. If you remember, I have discussed this, that tosyl chloride we use to convert a poor leaving group into a good leaving group. So what happens here, from this H and this Cl combines and HCl goes out, and we get a very good leaving group here, which is OTS. It's a very good leaving group, plus HCl we get. After this, the reaction with RMGX is similar that we have discussed. Okay, so what is the product here? Could you tell me? It is RCOH, R and R plus Understood? So when a poor leaving group, you can also say this is the reaction of carboxylic acid. So this poor leaving group, we convert into a good leaving group by some reaction, and then we have the same reaction like RMGX and H2O. Okay, these are three types of reaction of Grignard reagent, mainly this kind of reaction we have. Now we have so many reactions, like we have total 8, 9 different reactions of RMGX, but it depends upon all other reactions are similar to nucleophilic addition or elimination type. Okay, the fourth reaction you write down, the reaction with epoxide or epoxide reaction. In general, epoxide are those compounds which are 3-membered ring with oxygen present into the ring. This is epoxide. Generally 3-membered ring. It's not like only 3-membered possible. 4-membered also possible. But since we know 3-membered ring has maximum angle strain, hence it is most reactive. Okay, that's why we consider 3-membered ring. Now when this reacts with
This
R
is the
minus,
same as oxygen.
sorry, oxygen, yeah, right. The other name of it. 1 second, guys. This with H plus H2O, this is the reaction we have. The product of this reaction would be an alcohol, and that is this. This is the alcohol we get. How we get this product, we'll understand this. See, in the first step, what happens? This R minus has tendency to attack any one of the carbon atom, this one or this one. If this attack from this side, this bond comes over here and the ring opens up, right? And this forms this one, O minus and R, which on reaction with H plus H2O converts into an alcohol, that is OH. This is the product we have here. Important thing is what? You see the aldehyde, the alcohol that you are getting, in this alcohol, we have 2 carbon more than the carbon atom present in the alkyl group. Understood?
So one doubt.
Yeah.
So this is here. It's like
Symmetric.
symmetric epoxide. But
I'll come to that. Wait. Mechanism you understood? Right? Important thing here it is what? This R minus, this attack is SN2 type. This attack is SN2 type. Okay. And it always attack from the back side. So this addition of OH and R is anti-addition. It will be on the opposite side. This is very important. Okay. I'm not dictating this, but write it down in your own words. Okay. R and OH attached from the opposite side. Anti-addition. The attack of R minus is SN2 type. Okay. Now the answer to your question, Ruchit, since it is SN2 type, so it will always attack onto the less hindered side. Got it? So if branching increases at one of the carbon atom, the rate of the reaction at that carbon decreases. Correct? So if you look at this example of unsymmetrical epoxide, for example, we have CH3, CH, then CH2, and here we have oxygen attached with it. So reaction with RMgCl, H plus H2O. Could you tell me where this R minus will attack onto this epoxide ring? On this carbon or this carbon? The carbon which is hindered, right? On this carbon it will attack. This comes over here and this H plus comes over here. So if I could write down the answer directly, that would be CH3CH, CH2R, and OH. Okay, we are getting alcohol only in all these reactions. Now, the important point here you have to understand, or you have to keep in mind that first of all we are getting alcohol in this reaction. Okay. Now the number of carbon atom in the alcohol is 2 carbon, has 2 carbon more than the number of carbon atom present in the alkyl group. Very important this one. Okay. So the chain here is increasing. This is one point. Second point I told you already, SN2 type attack, anti-addition. Third point is what? If you have symmetrical epoxide, okay, the symmetrical epoxide gives you 1 degree alcohol here. Is it possible always that you'll get 1 degree alcohol in symmetrical epoxide?
No, sir. If you have any chain on that side on both of them.
That is also possible, right? So we cannot generalize this when we are getting 1 degree alcohol and when we are getting 2 degree alcohol. It is for sure that when you have unsymmetrical epoxide, then most probably you will get 2 degree alcohol, or primary you won't get basically. Okay, you can get tertiary also, secondary also, but primary you won't get. Okay, if you have unsymmetrical epoxide. Okay, so let's not generalize this that when we get 1 degree, 2 degree or 3 degree, but alcohol we are getting depending upon the reaction of epoxide, will be getting primary, secondary or tertiary alcohol. Here you see for this one I am getting primary alcohol. For the next one you see it is unsymmetrical. I am getting secondary alcohol. One more example, if I write down here, you see this CH3CH, single bond CH, CH3. Is it symmetrical epoxide?
Yeah.
Symmetrical. What is the product you get in this one?
So again, secondary unit.
Are you getting secondary?
Tertiary.
Tertiary?
Won't it attack? Okay.
But even that has a branch.
Yeah, same thing. So both have a branch, so we'll attack on either one.
Is it fine?
Yes.
So we are getting secondary only, no? Yes.
Just a secondary only.
Yeah, this R minus will attack onto this and this goes up. If this attack onto this comes over here. So we are getting secondary alcohol. So let's not generalize this that primary gives you symmetrical epoxide gives you primary or secondary. Okay, but addition will be anti and will get an alcohol. The alcohol will have more carbon atom than the carbon atom present in the alkyl group of Grignard reagent. Yes, Ruchi, tell me.
So if there's, let's say, one has more hindrance than the other, like, but that group is a electron withdrawing group.
Which one?
So like if we have carbon asymmetric, because one of them has more hindrance, but that hindrance is due to electron withdrawing group, then where will the reaction happen?
I didn't get you. Hindrance because of electron withdrawing group. Then, acha, you're talking about some carbocation formation and all.
No, sir.
It's SN2.
Just a second, wait. Yes, tell me. Richard.
Yes, sir. I asked if like one has more hindrance than the other, but that hindrance is due to electron withdrawing group. So will the reactions be faster there? Like,
Oh, I'll take an example. Okay, you are saying hindrance is different at different carbon atoms. These two carbon atoms, right?
yeah.
So suppose we have a group attached here. Suppose ET, CH, CH, and this side. What will take this side?
So any electron withdrawing.
Electron withdrawing group. How would you attach? Suppose NO2. If you attach this side, electron withdrawing group. This is what your question.
Yeah.
Where the reaction takes place. Electron withdrawing group has nothing to do anything over here. Obviously, ethyl group is the higher group. We have to see the hindrance at the alkyl group coming from this Grignard reagent with this group and this group. So obviously ethyl is a larger group, so this will produce more repulsion on the alkyl group coming from the Grignard reagent. So reaction takes place at this point.
So again, secondary alcohol, right?
Sorry.
So again, it'll be secondary alcohol. Anyway.
In this one also you'll get secondary alcohol. Okay. So here, Ruchir, we don't have to think for electron withdrawing or electron releasing because the reaction, in this reaction, there is no intermediate forming, no. It's one-step reaction, SN2 type. Correct.
Yes,
This
sir.
converts
Yes, sir.
into O minus and MgCl, and then in the second step, this H plus comes over here and we'll get alcohol. But this from here to O minus MgCl plus, that is, there is no intermediate forms. There's no point of talking about if there any electron withdrawing group present or electron releasing group present. Okay, just we need to see the hindrance.
Is this also ionic like the other ones that you taught us?
Ionic in the sense?
So like you said that it's
O minus MgCl.
no, so like it doesn't form any carbocation or anion. Is it like that?
Yeah, it won't form. It won't form any intermediate. SN2 reaction, you see, it is one-step reaction. No, there's no intermediate forms into this one. So this has tendency to attack onto this, and at the same time, this will come over here, and MgCl surrounds this O minus. That is it. Then in the next step, if you use H plus H2O, it converts into alcohol. Otherwise, it will be this with here O minus MgCl. There's no intermediate.
Okay, so.
Sir, is this how epoxides react with all nucleophiles? Or is it only Grignard?
No, this is, see, actually epoxide reaction, whenever you have a strong nucleophile present here, this will have tendency to attack on this carbon, depending upon the hindrance present at the two carbon. Why? Because this bond is polar, right? So this C plus will always attack any nucleophile towards it, any strong nucleophile if you have here. Here we are talking about the reaction of RMGX. This R minus is behaving as a nucleophile only. So it is possible with any nucleophile.
Yes, sir.
Okay. Yeah. So this is the reaction. Could you tell me the product in this reaction? How many products we get in this one? This with CH3 MgCl H plus H2. Number of product.
So should we type it out?
Should be?
Should we tell the answer or should we type it in the chat?
You can type, you can tell like whatever you feel comfortable. But I think there is noise from your side actually.
Yes, sir.
You can type better. Okay. So one of the product is this. Yeah, 2 is the correct answer. Okay. One of the product would be this. This ring would be as it is. There's no change in this ring. And this CH3 minus, it can attack onto this carbon and onto this carbon. Then we have equal probability of it. Okay. So the two possible product will be OH here. Sorry. It's fine only. OH here and hydrogen here. And then we have CH3 this side and H this side. Plus the another product is this. We have OH here, H here, CH3 always on the opposite, anti to this OH, H. These two are, you see, these two are mirror image of each other, enantiomers in nature.
So why won't there be optical activity here?
Where we have this one, optical active compound.
Oh, sorry, sir. I was confused.
Okay. So these two are mirror image of each other. right? And hence this is enantiomers. So any question they can frame in the exam, okay? They can give you in the options like the number of products will be 2, they are enantiomers of each other, reciproc mixture, optically active, anything they can ask you. Is this in a reciproc mixture?
Yes, sir.
Yes,
Yes,
it
sir.
will be a reciproc
Yes,
mixture
sir.
because we have equal probability of R minus to attack on the 2 carbon atom, correct? So this forms reciproc mixture. Each of these compounds is optically active. Overall, the mixture is optically inactive, okay, since it is a reciproc mixture. Okay, next reaction, the fifth one, the reaction of cyanides. The reaction of cyanides, and this one is a bit complex mechanism of this we have. And all these reactions that we are doing, you don't have to memorize the mechanism, okay? You need to know how to write down the product, especially for the carbonyl compounds, okay? If you are comfortable with mechanism, fine, but you should know eventually how to write down the product, because in the exam, if you're going to write down the mechanism, it will take a lot of time, okay? Now the reaction of RMGX, RMGCl with cyanide, that is R1C triple bond N, okay, we'll get a compound A which goes under acidic hydrolysis, H plus H2O gives B, okay? So what is this A and B? So first of all, the answer for this would be how to write down the product here. The answer for this would be here, the final answer is you take the alkyl group of Grignard reagent. Especially for this reaction, I would suggest that you should know how to write down the product directly, okay? R attached with this carbon, and this carbon has double bond O, and this R1 will be as it is. This is the final product of this reaction. Cyanide converts into ketone here, okay? So R1C, this carbon of cyanide will have double bond O, and this carbon attached with the alkyl group of Grignard reagent, okay? How it happens, we'll see the mechanism, but again, I'm telling you that you should know how to write down the product directly, okay? So first of all, what happens, this R minus, since it behaves as a nucleophile here, R minus MgX plus, R1 C triple bond N, okay? So what happens, this R minus attacks onto this carbon polar, and this comes over here, N minus, and this converts into R1 C R double bond N minus, and MgCl will be close to this, okay? This is A actually, this is A. Now after this, it's just the reaction of this with H plus H2O, right? Excess of H plus H2O we always take. So what happens here, this with H plus, right? It takes H plus, and this H plus protonates this nitrogen, and it converts into R1C double bond NH and R here. Plus with H2O we'll get here MgOHCl. MgOHCl. Now after this, just it reacts with H2O, and how to write down the product here, H2O, you'll write down here like this, HO and H, right? Write down like this. Carbon is less electronegative than nitrogen, right? So you break one of the bond here, right? One of the bond here, and this sigma bond you break. The less electronegative, that is carbon here, less electronegative carbon attached with more electronegative, and more electronegative nitrogen attached with less electronegative hydrogen. So with one H2O, the product will be R1 COH single bond NH2 and R. Again, we have the same thing with water, same reaction happens in the next step, and I am writing it down to make you understand. It won't happen in 2 steps actually. This again, it breaks, right? C goes with OH, N goes with H. The final product is R1. We don't have this. Okay. The final one is R1, COH, OH, R, plus we get ammonia, NH3. But in the next step, any carbon atom, the 2-hydroxy group, OH, on the same carbon atom is never stable. These two are not stable. Hence, one water molecule comes out from this, H2O combines with hydrogen here, comes out, and it converts into a ketone like this, plus H2. So this is the mechanism of this reaction. And this kind of reaction, the one I told you, carbon nitrogen, the more electronegative goes with less electronegative atom, and the less one goes with more electronegative atom. This kind of step, this one is very common when we have reaction of cyanide. Okay, in amines also we'll see this kind of reaction. Okay, so one by one these bond breaks. Okay, 2 double bond converts into NH3 plus diol. Diol 2-hydroxy group on the same carbon atom is never stable. Okay, this combines together, goes out as H2O, and double bond O will be here as it is. Clear? So how to write down the product? Okay, obviously you don't have to write down all these mechanisms. Okay, just you see R1C of cyanide with this carbon, attach double bond O plus the alkyl group of Grignard reagent you attach onto this carbon atom, you will get the product. Write down the product in this reaction. CH3 CH2 C triple bond N. PH MgCl with H plus H2O. Write down the product in this. I want you to write down the product directly. Okay, don't write mechanism. If you want for practice, you can do, but always keep this in mind that try to write down the product directly here. For practice, you can do for now. HCN with ET MgCl with H plus H2O.
Sir, could you move to the previous slide? I lost my internet connection.
Just a second.
Yes, sir. Thank you, sir.
Done?
Yes, sir.
Okay. Done, guys. The first one, the product is, this will be as it is, CH3, CH2, C double bond O, PH. What is the product we get here?
Aldehyde.
Propanol. Oh.
So
Why? Because this is acidic hydrogen. Remember the first type of reaction, acid-base reaction. Acid-base reaction is neutralization reaction, always faster than the other reaction. Yes. What happened? First wala reaction, you
Forgot
checked.
about that one. Yeah.
What term? Huh? First wala reaction, dekho Param. First wala
No,
acid-base
yeah, still
reaction.
I went back. Yes.
Huh.
Yeah.
Did you get it? So
Yes.
यहाँ पे क्या है? This hydrogen is acidic hydrogen, no? sp hybridized carbon atom, right? Hence here, the normal reaction of cyanide is not possible. We cannot eliminate that, but the chances are quite very, very less, okay? Because this reaction is extremely fast. I'll give you the comparison of it, okay? The priority order you write down. If you have the confusion of it, that which reaction takes place, then the priority of reaction is what? Acid-base reaction is the fastest one here. So wherever you have possibility of acid-base, that will take place. Okay, acid-base, the fastest reaction. Then we have nucleophilic addition or nucleophilic addition elimination. And then they won't give you to compare this to, okay, addition elimination. Don't worry for that. Okay. And the last one we have, that is SN2 type. SN2 type I'll just discuss now. It happens with alkyl halide. Okay, SN2 type. So here we have acid-base reaction possible. So this nucleophilic addition is not possible. Major product would be this. Minor also we don't consider because this reaction is extremely fast. Okay, so it won't form that. Got it?
So why did we hydrolyze it? Like the acid base, we don't have to hydrolyze, right?
Mm-hmm.
So like, why did we hydrolyze?
No, we don't need this actually. Just a medium, no, water, acidic is a medium in which the reaction is taking place. But this won't affect the product any much. Like because of this H2O only, we are getting OH, Mg, OHCl. So this H plus H2O is the medium we are taking. Once the alkane formed, this won't affect this, but this just helps this MgCl plus to get neutralized by having OH on it. Yeah, see what happens clearly. This will take this H plus. Okay, this will take this H plus from C2H6. Okay, and Cn minus ion will be there. Cn minus ion with H plus forms HCN exist in the form of ion only, H plus Cn minus. So that's why you don't need to write over there. And Mg plus get protonates from H2O forms MgOHCl. Okay, if you don't write H plus H2O also, you'll get the same product. It is understood that the medium of the reaction is this. In this medium only the reaction is taking place.
So if we didn't use H plus H2O, we'll get MgCnCl, right?
See, here also the possibility either this or this you may get. And it depends, see, how do you get MgOHCl here? Because when we have this Mg plus Cl, then water H2O behaves as a nucleophile, yes or no? Attacks onto this. And we get this MgOHCl. But if you have one more nucleophile present into the solution, this may also attack onto this. Correct. And forms what? This gives you MgCnCl, and this may gives MgOHCl. Okay. But here you consider both actually. Sometimes in the book, they have written this because it is the secondary product. No, it is not the main product. So we don't bother with this. What I am assuming here, that since water is a solvent, it is present in excess. Correct. So the tendency for this water to attack onto this MgCl as a nucleophile will be more than to that of Cn minus. That's why I have written this. But in some book, you see they consider Cn minus is a stronger nucleophile than H2O, and hence they give this product also. So either this or this, but the major product will be this one. Okay.
Yes, sir.
So, is it possible to make a hydrogen Grignard reagent?
Hydrogen?
Like, instead of RMgCl, can I make HMgCl? And will it do the same reaction?
HMgCl, no, it's not. I haven't seen that actually. Because HMgCl, H minus with Mg, it's not, see, the basic thing of the formation of RMGX, if you see, I have discussed in the first class that we have two ions, R minus and Cl minus X minus, that
Yeah, so
surrounds Mg2 plus, right?
Yeah.
So formation of H minus is difficult over there. Okay, so we cannot write H minus surrounds Mg plus and Cl minus surrounds Mg plus. I haven't seen that kind of reaction. It's not possible.
Okay, sir.
That's why you see it is an organometallic compound, no complex compound. So hydrogen does not involve in complex compound. We'll discuss that chapter also, coordination chemistry. There you see hydrogen is not involved in complex compound. Okay, so that's not possible. Next time you see the order I have given you, priority order. Wherever acid-base reaction possible, we'll consider that only. Okay. Third one, next type of reaction is SN2 type. Write down, this is the 6th type or 7th type, SN2. Number you write down, okay. SN2 type. SN2 type reaction, write down, it is possible generally with alkyl halide. Generally with alkyl, simple one it is. We have already discussed SN2 a lot in mechanism. So basically, if you have RMgCl plus CS3Cl, preferably we use here one primary halide, because primary halide has high tendency to go under SN2 mechanism, correct? So it goes under SN2 and it converts into RCS3, again an alkane, higher alkane, plus MgCl2. Okay, so with active hydrogen, it forms alkane. With alkyl halide, it forms alkane. But in case of alkyl halide, we get higher alkane. For active hydrogen, we'll get the same. We won't get higher alkane, but we get alkane with respect to the alkyl group of Grignard reagent. Clear? Okay, so for SN2 reaction, if they ask you to compare the rate, okay, compare the rate of, I've done this already, just for few practice, compare the rate of reaction of SN2 type. SN2 type reaction depends upon what condition? Tendency of leaving group, the nature of leaving group, CS3Cl, CS3Br, and CS3I. What is the order? Rate of reaction? Obviously, I minus is the best leaving group. Order of the reaction is this. Here we have branching, right? So this will decrease because of hindrance. SN2 type reaction decreases. Order is this. No doubt. Can I go to the next page?
Yes, sir.
Okay. You see, one very important question, and generally this kind of question they ask in integer type, JE advanced. Okay, look at this structure. This is a structure given. Question is, how many moles of Grignard reagent gets consumed for this molecule? Means suppose this molecule reacts with Grignard reagent, then how many moles of RMGX we use here?
So for that OH group, do we assume we're using that tosyl fluoride?
What?
So that OH group, we need tosyl fluoride for it.
No. Tosyl, I haven't written TSCl, no. See, first of all,
Oh yeah.
that
Sorry,
TSCl, I have given you that reaction, no. So there you have to consider that TSCl converts OH into a good living group, and then the reaction with RMGX. But here it is not given. I'm telling you that this reacts with RMGX.
Yes, I know.
Done? Three. Chaitanya got 4, Ruchir has got 6. Okay. 6. Okay. Okay. Fine. You see, first of all, 1 mole of Grignard reagent will use over here with Cl. And what is this reaction? This reaction is SN2 type. 1 mole, correct? Aldehyde, here we have 1 mole. 1 mole, it is nucleophilic addition. 1 mole we have here. With Cn, what happens?
So 2.
Why 2 in Cn?
It's 1.
The one.
Yeah.
Only one.
1 mole with Cn. And what is the reaction here? 1 mole with this acid-base reaction. Acid-base. 1 mole here, that is nucleophilic
Yes, sir,
addition,
1
and
mole.
1 mole here, that is
Yeah.
nucleophilic addition elimination. So we use here 2 mole of it. So how many moles total we are using? 2, 3,
6.
4, 5, and 6. 6 mole of RMGX we are using for this purpose. So this kind of question they ask in integer type, okay, JEE Advanced, okay, or in Mains also they may ask, okay, they can give you some simpler example, then how many moles of Grignard reagent we use generally. Okay, important. And this is not tough also, you can understand it easily. Okay, so this is one type. The another reaction, write down. The another reaction is reaction with halogen.
So does this come under SN2 or is this different?
No, it's different.
Okay.
It is a next type of halogen reaction. Kind of SN2 you can say, RMgCl with suppose X2, X and X. It forms Rx plus Mg XCl. This X could be X2, we can take chlorine, we can take bromine, we can take iodine, but it is not fluorine because fluorine has higher bond strength, very difficult to break the bond, right? It is delta positive, delta negative, this will attract onto this and this goes out as X minus, which gets attached with this MgCl. Okay, similar kind of reaction we have with HCN, and we know the product in this one. Okay, this is acid base type. So here we are not, no, we are not saying that this is one type of reaction, one particular type of reaction. Like you see here, it is mostly SN2 type, but here it becomes acid base type. Okay, and in this case, we'll write MgCN and Cl here if you use this, correct? Next, if you take ClCN, ClCN also gives RCN here. Why not RCl? Could you tell me?
Because CN is better nucleophile. No.
So
So
Cl
Cl is a better leaving group.
So
plug
because
in come
it's
up.
easier for Cl to hold the negative charge than for Cn.
See, here C triple bond N we have, no. So charge on carbon, the positive charge is, that density is high because chlorine is also electronegative and nitrogen is also electronegative. So this will attract the R minus most, this carbon atom. And hence this will attack onto this, Cl minus goes out, we'll get RCN plus MgCl2. That is not Advik. For the preparation of RMGX, we have Rx plus Mg in ether. It is not RMGX plus Cl2 there. It is alkyl halide with metal in presence of ether. No, it's not. No, it's not. If you have RMgCl, then how do you have RCl there? And there we have RCl first plus Mg in ether, which converts into RMgCl. So RMgCl with halogen, the reaction we have next. Means in that mixture, if you add chlorine, then what you will get. That is what the reaction is. I'll explain Varun just a second. Correct. Now, why your question is Cl and Cn? Correct. So Cl and Cn, you see, chlorine cyanide, it is this. So you have to understand the attack of R minus is easier on this carbon or on this chlorine. Easily you can understand both are electronegative element more than the carbon atom. So here the positive charge density is obviously more than the chlorine atom. And hence this R minus will attack onto this, Cl minus goes out easily. Understood, Varun? ClCN, if you see, it is a pseudo halogen compound. Yes or no? We have discussed pseudo halogen in P block. Okay, Cl2 type. Similarly, we have Cl. One Cl is replaced by Cl. Kind of that you can understand. That's why we have similar kind of reaction also with RMGs. Okay, one more very important reaction of RMG X with oxygen. Okay, the mechanism of this is it's a little bit weird. I'll tell you how the mechanism goes, but the reaction is very important. Okay, RMgCl plus O2, and it converts into alcohol. Okay, for oxygen we take 2 molecules of RMgCl and it converts into 2 molecules of ROH. Okay, how it happens? This R minus reacts with oxygen, O double bond O, and this attacks onto this, pi electrons shift onto this oxygen, and we get R O single bond O negative charge on it.
So
Okay.
there's equal
Yeah.
probability for it to attack on either oxygen, right?
Which one? What
So
probability?
like it can attack on either oxygen atom, right?
Any oxygen atom, not an issue.
Okay.
Any oxygen atom. So you see here, we have here electron-electron repulsion, right? So slightly when you heat this, in presence of another R minus molecule, right? If you heat this, then this bond breaks, right? And this R minus attach with the another oxygen, and this converts into 2 molecules of RO minus. Okay, this bond breaks, it comes over here. This R minus takes this and it converts into 2R minus, which on reaction with, in the next step, we use H plus H2O, 2 molecules of H plus H2O or excess of H plus H2O. It converts into 2 molecules of ROH. So H plus H2 will write down. So with oxygen, it gives alcohol. So basically in some of the book, what is given, that when you heat this, this oxygen takes this electron pair and the oxygen here becomes a vacant orbital here we have, where this R minus donates its electron pair and hence RO minus bond forms. Okay, so if you look at this in the book, they have written it like this. This goes over here and this comes onto this oxygen. Then the confusion is why this R minus is attacking on O minus. That is not possible, no? Minus and minus here. But it's not like it is attacking here. When this comes over here, we have a vacant orbital with this oxygen. And then this R donates its pair of electron to the vacant orbital of this oxygen and we get this. So 2 molecules of RO minus we get, which on acidic hydrolysis gives ROH. Clear? Okay. The next, this one is important. Okay, JEE they have asked this question once. Okay, because you see it's a different type of reaction. Important this one. Now the next reaction you see, organometallic compound. RMGX itself is an organometallic compound. But what is organometallic compound? I have discussed already. The compound in which carbon metal bond is present, right? So this compound contains carbon metal bond. Few informations you must have to understand this reaction. Okay, you must have to understand this reaction. Okay, in NEET and all, they won't ask these kind of reactions. Okay, for important. Okay, what information you should have, I am giving you here. So you see the metal like Li, Mg, then we have copper, zinc, cadmium, Hg. When carbon forms bond with this metal, okay, they can either form a strong base or weak base. Okay, so the elements of the S block, okay, first and second group, this when forms bond with alkyl group, like suppose we have RLi or RMg, these forms a strong base. This you should know, strong base. And this one forms weak bases. Weak base. Like we have RHg. These are weak base. So basically, when this is a strong base, so it has more ionic character than this side. Okay, it has more ionic character because of strong base. Forms ion R minus and Li plus easily. More ionic nature. And this one will have more covalent nature because it is a weak base. More covalent nature, cannot form R minus easily over here. Okay, R minus easily over here. Why I am discussing this? Because R minus that takes part in the reaction, you see all the reactions of Grignard reagent, R minus which takes part in the reaction, that may come from Grignard reagent, or they can also give you any source like this, RLi, RHg, like that. Okay, so from these ions, these molecules also will get R minus as we get from RMGX. Okay, that's why we are discussing this. However, you see RMGX also a Grignard, also an organometallic compound. Okay, write down next into this. These kind of compound, this is strong and weak base, write down. These kind of compound shows metal exchange reaction. Shows metal exchange reaction. Shows metal exchange reaction. And the reaction goes towards the weaker base always. And the reaction goes towards the weaker base always. Okay, goes towards the weaker base always. You see these reactions, two molecules of RLi, which is a strong base, reacts with a compound. So for example, CdCl2, it forms R2CD plus 2LiCl. This is not the actual reaction. I'm just giving you some information now. Similarly, you see two molecules of RLi when reacts with HgCl2 converts into R2Hg with 2LiCl. But when the same reaction takes place like this, R2CD plus LiCl, this converts into 2RLi plus CdCl2. All these are, you see, metal exchange reaction. Now what you need to understand here, that this is a strong base, and this converts into weak base, right? Weak base. All these are spontaneous reaction and possible. But here what happens, this is weak base and it is converting into a strong base. So weak to strong, the reaction is not possible. It is non-spontaneous. Okay. Yes.
What's the reason for that spontaneity?
It's just like I said, it's just a metal exchange reaction. Like we have acid-base reaction, that is neutralization reaction. No, exchange of ion takes place. Here we have exchange of metal. That is it.
Okay.
So the reaction doesn't take place at all.
Doesn't take place.
So it doesn't take place at all. The reaction, second one.
This one. It's not possible.
Yeah. Okay.
Not possible. Non-spontaneous. Okay. Now, based on this, you see what reaction we are here to understand. Okay. So this information you must have for these alkyl group and metal bond. Just need to keep in mind that these are a strong base and these are weak bases. Now you look at this reaction. Suppose we have a compound, and that is this. And double bond oxygen. Okay. Now this reacts with two different reagents. One I am taking the strong base, like, and from that strong base we are getting R minus, correct? H plus H2O. This is the reaction. This R minus we are getting from this strong base. And other one we have weak base, again R minus H plus H2O. Then what is the product we get? Since this base is strong, right? So this will attack onto this partially developed positive charge, this carbonyl carbon, right? So the product here, two different product, I'll write down with two different colors so that you can understand how the reaction goes. This attacks onto this partially developed charge because it is strong, right? And this comes over here. So the product is this. This double bond will be as it is, O minus R from the strong base, which goes under the reaction with H plus H2O, converts into OH and R. This double bond will be as it is. Okay. But now when it is a strong, when it is a weak base, so R minus has less tendency to attack onto this because the charge density is not great over here because it's weak. Correct. So what happens? This R minus waits for it. This will wait to get a completely developed charge. And how do we get the complete developed positive charge? When you draw the resonating structure. Okay. When you draw the resonating structure, you will get something like this. The structure you will get something like this, where here we have the double bond, here we have the positive charge and O minus. Once you get this completely developed positive charge, then this R minus from the weak base, this will attack onto this positive charge carbon, and this converts into O minus double bond and R here with H plus H2O. It converts into OH on the top, R here, OH on the top. Copy this down just a second. Hello? Yeah, I'm speaking. Yes, so this is the product we get. So two different products we are getting. If you look at this product, you know about these reactions. Okay, this is actually, this one is This one is the product that you get. And this addition, if you see here, we'll get one more product into this. This addition you see, first I'll write down, it is 1,4 addition. 1,4 addition. One more product I forgot to write down here. This further goes under tautomerism and it converts into this double bond O and R. This is tautomerism. Right, it can. So this is the final product, 1,4 addition. But this one, if you see, it is 1,2 addition. 1,2 addition is the KCP, kinetically controlled product, and this one is TCP, thermodynamically controlled product. Why KCP? Because you see here, this is a strong base, right? So it reacts so fast, it will attack onto this positive charged carbon atom, partially positive carbon atom. It won't wait to develop a fully, won't wait for this charge to develop, fully developed charge, correct? But since it is a weak, so it won't get attracted to this partially developed positive charge. The attraction is not that great, and hence this base wait for this charge to develop, which is a completely developed charge, and then the attraction will be more, and hence it will attack onto this and gives this product, which finally goes under tautomerism and forms this product, correct? So the second one is 1,4 addition TCP, thermodynamically controlled product we get, and the first one is KCP, kinetically controlled product. Clear? No doubt. We know one more thing. KCP is what? KCP is fast forming product, right? Fast forming product. And TCP is slow, but it gives more stable product. Done? Okay. Write down the product in this reaction. Could you tell me the product here? Just a second, guys. Copy this. Done? See, the first one we have a strong base. So strong base gives you 1,2, that is KCP, kinetically controlled product. So we can write down the product directly here. The position of double bond won't change, OH and R here. In the second reaction, what happens? We have RLI with CuCl2. This will react with each other and it forms R2Cu plus 2 LiCl. Now this is what? This is a weak base. So hence this mixture gives you 1,4 addition product, that is TCP, double bond O and R. No doubt. Okay, can you move on?
Yes, sir.
Okay. So now till here, I think we have the 9 or 10 reactions of Grignard reagent. These are the reactions possible with Grignard reagent. So whenever you get questions of Grignard reagent, whether it is a series reaction or what, you can think of all these reactions depending upon what reactant given. Okay. More than this reaction is not possible. Okay. So these are the reactions of Grignard reagent. Now in this chapter only, we are going to start the second part of it, that is oxidation reduction reaction. Okay, write down the heading, oxidation reduction reaction. So here we are going to do all oxidation reduction reactions that is given in organic chemistry. Okay, so we'll start with from the first chapter. Okay, it's not like we'll do for alcohol, aldehyde, ketone. We'll start from alkene. So wherever it is possible in the entire oxidation reduction reactions of organic chemistry. Okay, so we'll do reactions of aldehyde, we'll do reactions of ketone, for alcohol, for alkene, all these things we are going to discuss, right? So assignment that I have shared, okay, it is with this only, Grignard reagent, oxidation reduction. The two, I have shared PDF last class, 2 PDFs. Did I share yes last class?
No, sir.
No, I'll share after this class. Okay, and plus with this on Learnist also there are 2-3 PDFs you will get. Okay, I have already given it. Okay, maybe they are working on it, so they'll upload in someday. Okay, so you'll get there also the reaction. That includes this plus the reaction of Grignard reagent. Okay, fine. So the first reaction we are going to start with, oxidation reduction reaction. The first one we'll see the oxidation of, write down the oxidation of, we'll see oxidation reaction first, finished all, and then we'll finish reduction reaction. So we are starting with oxidation now, and we'll see the oxidation of alkene and alkyne. Okay, so I have discussed already these reactions in hydrocarbon chapter, but here we'll discuss a little bit more. We'll see the mechanism properly and we'll discuss questions on this. Okay, so first reaction you see, oxidation of alkene. The first reaction we have ozonolysis. We have done this reaction, ozonolysis, right? So ozonolysis, it requires what reagent? Could you tell me?
Zinc, I think.
Yeah, Zn.
Sorry?
So zinc.
Zinc and
Water.
O3.
Zinc
and
and water.
only zinc and water. Zinc and water we use in the second step. What we use in the first step?
O3.
O3, ozone. Okay. So you look at this reaction. Suppose we have an alkene that is R1, C double bond C, R2 suppose we have here, it is R3, and this is hydrogen. And all of you write down this because you feel like, okay, we have done it, so we won't write. It's not like that. We'll do this in detail, okay? So don't skip anything. So when this reacts with O3 with ZnH2O. We'll get one product. One more reagent we use, and this one we haven't done. That is O3 with H2O. Correct. Now, what is the difference between the two? Could you tell me the product in the first one?
The ketone and aldehyde, R3CHO and R1CO2.
This is the product we get. And we know how to write down the product. Just we break this double bond and attach oxygen with these two carbon atom with a double bond like this. Okay. When we do not use zinc, then the product is R1C double bond O, R2 plus O double bond C, R3 and H, right? But here this product is not the final product. Further, you get oxidized into carbon with R3 here and OH. This is the difference in the two reactions. When you do not use zinc, you will end up getting acid. Ketone to form hoga hi hoga. There's no difference in this, correct? But aldehyde we won't get into this reaction. If we do not use zinc, no, it's not a poison here. It is used to extract oxygen. I'll discuss the mechanism. Wait. Okay. So this is the reaction. So first thing what you need to keep in mind that when you use zinc, you will get aldehyde if it is possible. When we do not use zinc, you won't get aldehyde. Ketone forms as it is. Okay. Actually, what happens here? First aldehyde forms and then it further get oxidized into acid. But here the further oxidation is not possible. Okay, because there is no any oxidizing agent present because of this zinc. I'll discuss the mechanism also. You see, the oxidation of ketone is not that easy. Ketone I have discussed already in biomolecules that it get oxidized in drastic condition. We require very strong oxidizing agent. That's why the presence or absence of zinc won't affect ketone, but it can oxidize aldehyde and gives you acid. So this is the basic difference in the two reactions that you should memorize. If you keep these things in mind, you can do all the questions, correct? Now, the reaction that I have written here, okay, this reaction, when we use zinc, this reaction we call it as reductive ozonolysis. It is reductive ozonolysis. When we do not use zinc, this we call it as oxidative ozonolysis. Right? So ozonolysis we also have two types, reductive and oxidative. Reductive ozonolysis, if possible, gives you aldehyde. Oxidative aldehyde. That is the difference. The difference in reagent is what? In reductive, we are using zinc H2O. In oxidative, we are not using zinc. So how the presence or absence of zinc affect the product of the reaction, that we should understand, right? And we can understand this once we see the mechanism of this reaction. So let us discuss the mechanism of this. Mechanism of ozonolysis. Okay. If you look at the structure of ozone, the structure of ozone is this, right? Oxygen has negative charge, 3 lone pair here. Here we have positive charge, only 1 lone pair. And here we have 2 lone pair. When you draw the resonating structure of this, it converts into O, single bond O, oxygen, single bond O, O, negative charge with 2 lone pair and positive charge, right? Because this bond comes over here, we'll get this. Okay. Now this one, this we call it as oxygen positive charge. This is electrophilic end of ozone. electrophilic end, and this one is the nucleophilic end. There are so many reactions we are going to discuss in this section, and most of the reactions has similar kind of mechanism. Okay, so it's very important to understand. Now when it has two end, electrophilic and nucleophilic, how does it react with the alkene? So what happens, this oxygen with the two different end, okay, comes closer to this alkene like this. This is negative, this is positive, and when this attacks onto this carbon, this pi electron shift here, and this will attack onto this oxygen, and hence it converts into what? It converts into compound which we can draw this way. Okay. In the book, this structure is not given. Okay. What structure is given, I'll show you. This structure, we call it as molonozide. M-O-L-O-N-O-Z-I-D-E. It is molonozide. This structure is. Correct. Further, this structure, molonozide, converts into this. This bond breaks, this sigma electron comes over here, and this pi electron goes onto this oxygen. This sigma electron goes onto this oxygen, and this bond breaks. So it converts into this. We have carbon with oxygen double bond, plus next we have this carbon here with two bond and 2 oxygen like this, O negative charge. So what happens next, you see, since this carbon has positive charge, you see, because this bond pair of electron comes over here, so this carbon will have the positive charge. So this lone pair on this oxygen, I'm talking about this oxygen, this lone pair, it attacks onto this carbon, and then this negative charge or this pair of electron attacks onto this carbon. And hence this converts into a structure which is given in the book, that is this. Yes, and this structure is ozonide, if you remember that. It is ozonide. Okay, and then further what happens, when you heat this with zinc, it converts into aldehyde or ketone. So how does it go? You see here. This electron pair comes over here, this comes over here, right? And this bond pair goes onto this oxygen. So it converts into 2 molecules of C double bond O, and this oxygen comes out as the nascent oxygen. Nascent of this vacant orbital. Okay, this happens. So we'll get this product. Okay. Now this nascent oxygen is responsible for the oxidation of aldehyde into acid. Okay. So if you do not use zinc here, this will be present, and this nascent oxygen further oxidize aldehyde into acid. But when zinc is present, sorry. Hello?
I have a doubt.
Just a second, let me finish, we'll discuss it, okay?
Okay.
So this nascent oxygen is responsible for the oxidation of aldehyde, if it is present, okay? Now, if zinc is present there, so what happens with zinc? Zinc will extract this oxygen. It helps in elimination of this oxygen. So zinc extracts the nascent oxygen and forms zinc oxide, ZNO. If zinc is not present, this will be there in the reaction, and this will oxidize aldehyde into acid. This is the mechanism of this reaction. Yes, Ruchir.
So if both products are ketones, then it doesn't matter if you have zinc or right?
Doesn't matter, yes. Because like I said, ketone oxidation is very difficult. There are only few reagents which can oxidize ketone. Okay, we'll discuss that. Baeyer-Villiger oxidation is one important oxidation reaction of ketone that converts ketone into ester. We'll discuss in this chapter only. Okay, otherwise the oxidation of ketone is very difficult. So if both the products are ketone, whether you take zinc or you do not take zinc, it won't affect the product of the reaction at all. Understood? This molanoxide, we also call it as initial ozonide. Initial ozonide. Yes, Dhruv, just a second. You'll get a break after finishing this. Let me finish this reaction. No doubt. So oxidative and reductive ozonolysis, you must remember. Oxidative ozonolysis in absence of zinc, reductive ozonolysis in presence of zinc. Okay, oxidative ozonolysis, you won't get aldehyde as the final product. Ketone will get, it won't affect the presence of ketone. Okay, so based on this, we'll see some examples. Okay, and it's very easy to write down the product in this reaction. Suppose for this one, CH2, it goes under reductive ozonolysis, O3 with ZnH2O. This goes under oxidative ozonolysis. Double bond C, CH3H, and this is O3 with H2O. Sometimes they ask question like this: what is the reagent we should use which goes under reductive ozonolysis and converts into this product and gives this product? What is the reagent we use which goes under reductive ozonolysis and converts into this? Write down the product in all these reactions.
Yes, sir, could you go to the previous slide, sir?
Done? Mehul, done?
Yes, sir. Now I'm done.
Sir,
Yeah.
should I text the answer? There are so many answers.
You can. You can send me the picture. All of you done, tell me.
Yes, sir.
Okay. So what we need to do, mechanism is fine. We understood the mechanism, but yes, in the exam, you don't have to draw the mechanism. Okay. What you need to do, just need to break this double bond and attach oxygen with the 2 carbon atom with a double bond. That is this. Okay. Yeah, correct, Ruchir. Okay. This also we have the same thing. We have cyclohexanone, right? Plus O, double bond C,
The CH3COH, right?
just a second. I was looking at the answer of this one.
Yes, sir. You're done.
So you'll get this, but here you won't get hydrogen, but we get here. Why? Because it is oxidative ozonolysis. Clear? That's what you have written, Ruchir, right? Yeah. Okay, we won't get aldehyde into this. This too, we have to just eliminate oxygen and attach the 2 molecule, right? So the product is this. Here also, just you remove all these oxygen and attach all the molecules with a double bond. So we have CH2 double bond C, CH3, CH3. Okay, this is the answer for this. Could you tell me the reactant molecule which gives the product in oxidative ozonolysis, and the product is this? They can also ask you what is the reagent here. For this to this conversion, what is the reagent we use? Tell me the product in the first one. See, in the first one, the product is this. CH2, is it? Methylene group attached to the cyclohexane. Okay, why this? Because you see, how do we get this product when it goes under oxidative ozonolysis? One of the product we get is cyclohexanone, and the other one is O double bond C and OH here. Yes, and since 2-hydroxy group on the same carbon is not stable, this eliminates water molecule and converts into CO2 and H2O, and hence the product is this and this. Okay, in this one, the product would be like this. Double bond O and double bond O. This looks like if you add double bond O here and double bond O here, that is also same. You look at this position first of all, because they give you the option like this. Okay, so this is also correct answer. How? I'll tell you. 1, 2, 3, 4, 5, and 6. At first and sixth carbon, we have double bond O, right? Here also you see 1, 2, 3, 4, 5, and 6. This is the most stable structure. The distance between the oxygen atom is more, and hence this structure they can give you in the option.
So sir, if both are given, like suppose it's a single correct and both are given, we'll choose
No,
this
both
one, right?
they won't give first of all, right? If they give both, then both will be the answer for the question, because you see, if you add double bond O here, double bond O here, both are first and sixth position, no?
Yes, sir.
Right. So, and this is also first and sixth position, right? So they won't give both. If they have given both and only one choice you need to select, right, then you should go with this, because when you attach double bond O here, there will be a lot of repulsion, right? Hence that
Yes,
structure
sir.
won't be stable. Hence they will rearrange itself in this way. Actually, double bond O double bond, if you place over here, it's a rearranged structure, and in this way it is the most stable one.
Yes, sir.
Yeah, that one is wrong, Dhruv. You do not have C double bond O here. Double bond C, double bond O is not possible. You cannot do that. Okay. This one. So this you must keep in mind, this kind of a structure. Now you see this molecule is given, correct. Sometimes what happens, they'll give you the condensed formula of it. Means they'll give you, oh, I forgot to write 2 molecules of this we have. Sometimes they'll give you this. Not sometimes, they will mostly gives you this structure. But then since structure is not given, then it is difficult to write down the answer. Why I have given you this structure? Because I haven't given you the option. But with option you can understand. First of all, if this is given, then we can find out DOU. What is DOU for this? That is 3 you will get. Once you use the formula, you'll get 3 DOU. Okay. So with that value DOU, you will have a bit of idea that what is the possible structure. Plus the option will be given with you, A, B, C, D, 4 options. With that, you can understand that what is the possible, structure of this particular product. Okay. But here it is easy, since I have given you this, you can write down this molecule as this way: hydrogen with carbon, single bond carbon, single bond carbon, hydrogen. We have double bond O, double bond O, double bond O. Since oxygen we have to eliminate, so I'll write down the 2 molecule this way. Correct? And hydrogen placed this side. So we have to eliminate hydrogen, oxygen, right? So we eliminate this 2, this 2, this 2, and attach the oxygen carbon with a double bond. So that would be what? C, 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 double bond C, double bond C, and double bond C. And all these terminal carbon has 1 hydrogen present. And the answer or the structure given in the question, that would be like this. These 2 are same structure. Yes or no? So little bit if you think on the option, you'll understand that what could be the possible structure of A. Clear? No doubt? Fine, guys, we'll take a break now. And after the break, we'll start with the rate of this kind of reaction. Okay, we'll resume the class at 6:30. Take a break now. Hello? Yeah. Okay. So we have discussed all these examples. Next one you see, uh, the rate of ozonolysis. How do we compare the rate of ozonolysis? See, ozonolysis, we see there's a positive charge on carbon atom forms during the mechanism. So it is a type of electrophilic addition reaction. Electrophilic addition reaction. And the rate of reaction, hence the rate of reaction ROR is directly proportional to the stability of carbocation. Okay, so for example, ozonolysis of this and this, if you compare, alkene and alkyne, if you compare, so always on alkene the rate of ozonolysis will be more because it is sp2 hybridized, less electronegative. So positive charge here is more stable. Here the positive charge more stable because of more number of alpha hydrogen, and hence the rate of ozonolysis will be more. Okay, so alkene shows, in this you write down, alkene shows faster rate of ozonolysis. Okay, done. Okay,
So just 1 second.
So what happens when alkynes get ozonolized?
we'll discuss that. It's not that important, but in the last we'll see. Carbon-carbon bond does not dissociate into that. Okay, just simple thing. If you have alkene, then the two bond dissociates, pi and sigma, between the carbon atom. Here also the two pi bond dissociates between the carbon atom, but sigma bond will be there as it is. And double bond O attached with the carbon atom, we'll see that reaction. Okay, now could you tell me which one is which one has more rate of reaction in this two?
So the first one.
First one, more alpha hydrogen, more stable carbon. Okay. For aromatic compound, how ozonolysis takes place into this, you see that. Aromatic compound, we have benzene ring, and this goes under oxidative ozonolysis and reductive ozonolysis, O3 with ZnH2O, and the second reaction of this we have O3 with H2O. So here what happens, all the triple bond, all the double bond you have to break. You see sigma bond won't break here. Okay, you see this carbon-carbon bond won't break, this carbon-carbon bond won't break, and this carbon-carbon bond won't break, right? Carbon-carbon double bond here, ozonolysis takes place, here also ozonolysis takes place, and here also ozonolysis takes place. So this carbon and this carbon will have this bond as it is. So we have carbon-carbon bond present like this, and this carbon has double bond O, this carbon has double bond O, So double bond O, and hydrogen is already present on this carbon atom. And this also gives you the same product. This carbon-carbon bond also gives you the same product. So 3 moles of this we get. The name of this compound is glyoxal. Similarly, if you have oxidative ozonolysis, then this H converts into OH. That is it. Okay, and this compound is oxalic acid. Important, this reaction, sir. Okay, now what you have to understand, you see, this compound is aromatic in nature, right? And when it goes under ozonolysis, it loses its aromaticity, which is no, that's why the reaction is extremely slow. This reaction and this reaction both are extremely slow reaction because the compound is losing its aromaticity. Right, we can neglect this reaction also, but since here we do not have any possibility, so we have to write down this product. There's no other way. Okay, there's no other possibility, there's no other options. But suppose if you have a compound like this, suppose we have a compound like this, okay, and in this, if you consider ozonolysis, reductive or oxidative, that is not a discussion. Okay, then the ring does not go under ozonolysis reaction, the aromatic compound. Reason is same, it is extremely slow reaction. So if you have other option, the ozonolysis takes place at that particular carbon atom. So here the ring retains its aromatic behavior and we end up getting this compound, double bond O and H here, plus O double bond C, H. No doubt?
1 second. Yes, sir.
Done. Okay, so always keep that in mind. If you have any other option, then the ring, aromatic ring, does not go under ozonolysis. But if you do not have any choice, then we'll have the product this. Okay, the last part of this, where we have ozonolysis of alkyne. Like I already said, alkyne goes under ozonolysis reaction exactly like alkene goes, but only the difference is.
So could you go to the previous code just one? So thank you.
Okay, alkyne, like I said, like alkene, we don't get two different product here. We get only one product, only pi bond breaks into this. So for example, it is not that important. The alkene reaction is far more important than this. O3 with ZnH2O gives you R1C double bond O, C double bond O, R2. If you have HC triple bond C, R with oxidative ozonolysis, then you get HOC double bond O, double bond O, and R. This is the product.
So in that previous example, you gave us something which looked something like this. So how would we know if it's an alkyne or an
Which
alkene?
one? This one or previous one?
So like before you gave us some questions on ozonolysis, right? It was before this also. So it was before the break.
Which one? Could you tell me the example?
Yeah. So
the one in which you can
Yes,
write it
yes,
as this one.
That gave
yeah.
2 moles.
So over yes. So this one. Here, how do you know that this is not an alkyne?
Which one?
Can't
This one?
have trip 2
Yeah.
double
Yeah.
bonds,
Okay.
right?
Yeah.
Okay.
Yeah.
Okay.
So
Chalo,
that's
ठीक है.
yeah. So
Is it possible?
it's not. So I didn't remember that there were 3 oxygens. Yeah.
So it's fine,
What
no?
if there's triple bond between like only 2 of the carbons and the
Right.
fourth bond?
Okay. Is it clear?
So, but like if we only had 2 of them, then can we?
If you have 2 of them, then we can have the possibility. Then we can discuss. Okay. Suppose if you have
So
only
it's 2 moles, right?
This one is giving 2 moles.
no, fine. Obviously, if you have 2 over here, then they won't give you 2 moles. It depends. No, if you change, the thing will change, right? Suppose if you have questions, the product, if it is like this, HC double bond O, C double bond O, and then we have suppose suppose CH3. Correct. Then if they give you this, they won't give you 2 moles. So here for this question, first of all, if you place a triple bond, that is not possible. And since it is 2 moles, it means we are getting 2 compounds of it from the one compound, that is alkene. Clear?
Yes, sir.
Okay. So the alkyne ozonolysis reaction is not that important, but yes, it is simple. Just you need to break the pi bond and attach oxygen like this. Okay. Now the next reaction, the second reaction of oxidation of alkene, that is, write down hydroxylation reaction.
So for oxidative ozonolysis for alkenes, there has to be a H present.
There must be?
There must be a H present, right? Like you can't have 2 alkyl groups.
No, you can have R also, but that won't change the product, whether you do oxidative or reductive.
Okay.
Okay, you can have, I have written here to make you understand that what happens if you have oxidative ozonolysis.
Okay.
If you, here also in the first one, if you do oxidative, you'll get the same product.
Okay.
Yeah. Okay, so the next reaction, like I said, hydroxylation reaction. What is hydroxylation reaction? Write down. It is the addition of the hydroxy group. It is the addition of hydroxy group on both double bonded carbon atom. Addition of hydroxy OH group on both double bonded carbon atom. Okay, look at this example. This hydroxylation actually, it can be syn or anti, both possibility we have. Okay, syn addition or anti addition also possible. So a little bit here in oxidation reduction reaction, a little bit the property of reagent you have to memorize. Okay, and we don't have no mechanism of all the reaction. It's not like mechanism is not there. Some other book like Peter Sykes or SN Sanyal, if you study, there are mechanism given, but those mechanisms won't help you. You cannot draw those mechanisms, write down those mechanisms in the exam and write down the answer. Correct. So the best way is what you have to memorize, that how the addition takes place and how we get the product in the reaction. Okay, wherever mechanism is there, I'll discuss, but few properties of reagent you have to memorize, like whether it gives syn or anti addition. So this is the reaction we have, syn addition or anti addition. Now you should know what all reagents gives syn addition. What all reagents gives? Anti-addition. Okay, so write down the next line here. Reagents for syn hydroxylation. Reagents for syn hydroxylation. Means when OH attached from the same site. We have two reagents here, right? And the mechanism for both are exactly same. The first one is dilute alkaline KMNO4. This reagent, we also call it as Bayer's reagent. Bayer's reagent. Okay, and it is of purple color. Aqueous solution of it is of purple. Okay, purple color. So KMNO4, you see, it dissociates into its ions. So first of all, it is Bayer's reagent, and it is Bayer's reagent test also it gives. Okay, what is the test? I'll tell you. Okay, KMNO4 actually, it dissociates into K plus and MnO4 minus. MnO4 minus, the structure of MnO4 minus, if you see, it is this. Mn double bond O, double bond O, O minus, and double bond O here. This is MnO4 minus. When you draw the, okay, since it is a metal, so it can take, for reaction what happens, it takes this pi electron and this develops a nucleophilic and electrophilic end, O plus and O minus. Right? If you look at this part, this looks like ozone, correct? The same kind of structure, right? Ozone also has nucleophilic and electrophilic end.
So charge is not the same, right? Overall charge. Shouldn't Mn
No,
be?
this Mn will have negative charge.
Yes.
Okay. Now you see what happens. This interacts with alkene similarly like ozone interacts, right? So we have C double bond C, suppose just a second. We have C double bond C, and this MnO4 minus here, it has, like I said, both electrophilic end and nucleophilic end. So this interacts with the alkene this way, right? This goes onto this carbon, this comes over here, and this comes over here. So we have an intermediate, which is nothing but this. O, Mn, O, double bond O, double bond O, and this will have, this is the compound we get, right? Now, which goes with H plus H2O in the last, it converts into OH, OH plus MnO2 we get. Copy down this. Done?
1 second, sir.
Okay. So what happens here? You have alkaline solution of it, dilute alkaline solution of it. Okay. The color is purple. When you add an alkene into it, the solution becomes colorless. Purple to colorless. This is the test of alkene, or test of unsaturation also we call it as. And this test we call it as Bayer's reagent test. Bayer's reagent test. It gives syn addition because it is a molecule, it attached from the same side of the double bonded carbon atom. Hence, we have the syn addition. Done. All these mechanism you don't have to memorize. Just you should know that dilute alkaline KMnO4 gives syn addition. OH group attached at the double bonded carbon atom. Okay. Now the second reagent we have here, which shows syn addition, that is osmium tetraoxide. Osmium tetraoxide, OSO4. Osmium tetraoxide. OSO4, if you look at the structure is exactly similar to MnO4 minus, but this one is neutral. But
so
the
which
pattern is
group is this one element?
Sorry?
So which group does this element come in?
Osmium.
Yes, sir.
Osmium is present in which group? It is a transition element.
Okay.
Oh, just a second. Osmium, no. Osmium has, it's a transition element. This can show the maximum. I think it is in this group. Group you have to see, but the third,
The eighth group.
Third series, you have the fourth column. If you see in the fourth column, a 4D series element it is, I guess. 4D series. You have to see the exactly what group it is. But
Okay.
one thing is very famous for this. Osmium is the element which can show the maximum oxidation state, and that is +8. Inorganic में ये question पूछा है बहुत बार. Which of this can show maximum oxidation state? So +8 is for osmium. This can show maximum oxidation state. Group 8. Yeah, that's right. Okay, so this property you remember. Okay, so you see what happened. It is a transition element. So it has the tendency to take this electron pair, and again it forms nucleophilic and electrophilic end. Okay, so OS, O plus, and this is minus, double bond O and double bond O. After this, it again reacts with alkene similarly like KMnO4 does. Okay, this is the end. So it will attach from the same side with alkene with H plus H2O, it converts into diol, correct? Do I need to write down the mechanism?
No need, sir.
That's the same thing. One thing I just corrected here, H plus we do not use, we use only H2O. Alkaline medium we have no. We use only H2O here, not H plus. In the same thing we have in the next one also. After this, when we attach with the alkene, we use hydrolysis, H2O gives you the product. Okay, now the important thing in this, because we know these two reagents give syn addition. Okay, so how to write down the structure of the product? Okay, so look at this example here. We have C double bond C, CH3, H and H. Okay, so whether you take dilute alkaline KMnO4 or osmium tetraoxide, you'll get syn addition. Okay, so the product is what? The product is, if you write down the Fischer structure, the Fischer projection, it is this. OH on the same side, H, H, CS3, CS3. This is the Fischer projection. Okay, so this is the Fisher projection of this. Now, when you look at this structure, this is a meso compound, yes or no? Meso compound and optically inactive, right? So syn addition gives you meso compound, and this one also you see OH on the same side, so it gives you erythro. Okay, so what you have to memorize, cis on syn addition gives erythro compound, CSE. Yeah, due to internal compensation. Okay, optically inactive due to internal compensation, plane of symmetry we have here. So CSE, cis syn addition gives you erythro compound. Okay, copy this down. I'll go to the next page. Okay, next one you see. If you take trans, that is HC double bond C, CH3, H and CS3, trans with the same reagent, it gives this product, trio, OH, OH, H. Addition is syn only, but we'll write down the Fisher projection this way. It is not anti-addition, it is syn addition, but you'll get trio. So trans on syn addition gives trio compound, TST. And this is what you see, it is optically active. And we get a mirror image of this also. Okay, one more product we get here, this plus this. Mixture as a whole forms racemic mixture. Mixture as a whole is optically inactive, but each of these compounds is optically active. Okay, so in trio we'll write both OH on the opposite side. The addition is what? The addition is syn only. We'll just write down the structure this way. Okay, so for syn addition, you need to memorize CSE and TST. Syn hydroxylation, CSE and TST, you have to memorize. Okay, cis on syn addition gives trio, you know OH is getting attached. Okay, so cis on syn addition gives erythro, OH on the same side. Trans on syn addition gives trio, OH on the opposite side. Okay, now the second one is anti-hydroxylation. Anti-hydroxylation. Write down the reagents which gives anti-hydroxylation are first of all, we can use the reagent, we can use any peroxy acid we can use with acid hydrolysis, H plus H2. Okay, any peroxy acid we can use. For example, we can use MCPB, metachloroperbenzoic acid. Metachloroperbenzoic acid structure you should know, but it is not that important. C double bond O, 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 H, and meta position we have Cl, chlorine present here. One more reagent we use, that silver with oxygen, this also with H plus H2O. H plus H2O. Okay, the mechanism of both are same, right? They both generates nascent oxygen. Okay, how you see this? Suppose you have any peroxy acid, RC double bond O, OOH. This on heating it gives acid and eliminates nascent oxygen from this. That is the property of peroxy acid. It eliminates nascent oxygen. Now this nascent oxygen, since it has one vacant orbital, so this also behaves as electrophile and nucleophile at the same time. For example, you see, we have nascent oxygen, right? So vacant orbital has tendency to accept electron. This lone pair it attacks onto this. This comes over here, and this has tendency to accept electron into this vacant orbital, right? So it behaves as both electrophile and nucleophile, and hence this converts into an epoxide, which is this. Now epoxide in acidic medium, what happens? It protonates the oxygen, OH plus, it protonates the oxygen, and in the next step, water, H2O, behaves as nucleophile, attacks on one of the carbon atom where the hindrance is less, and this bond, the ring opens up, and it converts into, and it attacks from the opposite side. Okay, the same thing for epoxide, R and OH. Remember that R, RMGX and OH, R and OH attached from the anti side, right? Opposite side. This also attacks from the opposite side of this ring, and it converts into COH this side and COH this side, anti-hydroxylation. Done? Okay. The reaction of Ag oxygen with silver with H plus H2O, it is also the same. You see here, silver reacts with oxygen and it converts into silver oxide, and again a nascent oxygen eliminates here. Then again we have the same mechanism like we had in the previous one with nascent oxygen. Okay, but you should know how to write down the product here for cis and trans alkene. So here we have CH3, C double bond C, CH3, H, H, on reaction with any peroxy acid, RC double bond OOH, H plus H2O. Okay, I'm just writing down the product. So here we have cis alkene. So what you have to memorize, cis on anti-addition gives trans, sorry, 3O, not trans. Okay, so what is the product we get? This is the product we get. Got it? So cis anti-addition gives 3O. This one again what? Will have a mirror image of this. So enantiomers, racemic mixture, optically inactive. So exactly opposite of the previous one. Okay. Similarly, if you have trans here, that CH3, C double bond CH, CH3, H, with the same reagent, it gives meso compound. OH, OH, H, H. Remember the addition is anti only. It is not cis. So trans addition gives erythro, meso compound, optically inactive. Done. Okay, so if it is hydroxylation reaction, then what you have to memorize? If it is cis, okay, see, you must remember this cat and tay, correct? So cat and tay you must keep in mind. Cat and tay. The only one thing you have to memorize. A stands for anti, anti, C is cis, and this is trans, right? So when this anti becomes cis, sorry, anti becomes sin, A become S, then E becomes E. You have to exchange this. And when this again, A become S, E becomes T. This is trans only, and this is cis only. So with this cat and tay, we can memorize this also. If it is anti, you already know cat and tay, we have already discussed it. So if it's in this cat and tay, A stands for anti. If anti becomes sin, then T becomes E, and E becomes T. Okay, with these two things, you can memorize all these reactions easily. Done. Yes, Ruchir, what happened?
So by mistake I pressed that, sorry.
Okay. See, Pranav, I have discussed the mechanism. Right, entry hydroxylation when 2OH on the it's clearly you can see you are getting an epoxide ring, and on that epoxide ring H2O behaves as a nucleophile attack from the opposite side. Correct. So 2OH is coming from the opposite side. That's why it is anti-hydroxylation. And erythro is what? Erythro is when the 2OH group present on the opposite side in Fischer projection. One OH on the right, then the other OH on the left. So in Fisher, if the 2OH on the opposite side, it is known as trio compound. I'll show you this way. When 2OH on the opposite side, it is known as trio, like this. This is opposite side, so it is trio. When 2OH on the same side, it is erythro, right? Because it is anti, so when you look at the structure of this, they arrange itself and we get this structure here. So when you get this and convert into Fisher, you will get this structure. So you should know the conversion of Fisher into Newman into Sawhorse, all those things I have discussed. Okay. So, and that's why, you don't have to think always what we'll get here. That's why I have used this cat and tay method so that you can write down the product directly. Okay. So this is the reaction. Now the another reaction of alkene is oxidation. We have discussed two reactions so far, that is ozonolysis and hydroxylation. Okay. Third reaction of alkene, you write down oxidation of alkene with acidified KMNO4 or acidified K2Cr2O7. They both are a strong oxidizing agent. Okay. Write down this reaction. This reaction is similar to oxidative ozonolysis. Both are very strong oxidizing agent. Okay. So again, the mechanism here, we don't have to do. We can eliminate that part mechanism. We just know how to write down the reaction in it, like the product in it. That's what I have discussed already. There are so many reactions and the mechanism is quite complex. But if you want, it is given in some book, I can show you that. Okay. But eventually you have to memorize it so that you can write down the product easily. Nothing much, like we have already done ozonolysis. Suppose we have this alkene and you are doing the oxidation with acidified KMNO4 with H plus. Okay, just you need to break the double bond and attach oxygen, similar to oxidative ozonolysis. So you won't get aldehyde here. You get C double bond O, OH plus will get O C double bond, single bond OH, single bond OH, which further dissociates into CO2 and H2. Okay, exactly similar to that. Could you write down the product in this one? Remember, it is similar to oxidative ozonolysis. Okay, K2Cr2O7 H plus. Product. In the first one, the product is cyclohexanone and CH3COOH, acetic acid. In this one, OH double bond O, double bond O, OH. This is the product we get. Done?
Yes.
Okay. Next, write down oxidation of alcohol.
So could you go to the previous page? Just 1 second. So over here, why does like in the second one, why does it form CH3C?
It is oxidative. So you won't get aldehyde. It converts into acid. Ozonolysis, we have discussed oxidative and reductive.
Oh, yeah. So, yeah,
so aldehyde won't form. Okay.
Okay. Yes. Sir.
Okay. Next, write down oxidation of alcohol. Oxidation of alcohol. See, in this one, there are so many reagents in this, and you have to memorize those. I'll give you some important one. Okay. There are strong oxidizing agent and mild oxidizing agent. Strong oxidizing agent mainly we'll discuss 3, and rest all are mild oxidizing agent. Okay, around 8 to 10 we have. Okay, and you have to just know that what happens with strong and what happens with mild. You'll get the product reaction directly in the exam. Okay, so a few general things you should know about this. If you have 1 degree alcohol, this goes under mild oxidation. Mild oxidation, or you can say controlled oxidation. This gives you only aldehyde with mild oxidation or controlled oxidation. But if you have very strong oxidation of this, on a strong oxidation or very strong oxidizing agent if you use, then it converts into aldehyde first, then aldehyde further oxidize into acid, carboxylic acid. Okay. Second one, if you have 2 degree alcohol, whether you use mild or a strong oxidizing agent, it converts into ketone. Okay, 2 degree alcohol always gives you ketone. 3 degree alcohol does not go under hydrolysis. Sorry, no oxidation. No oxidation for this. But this will get, elimination. By elimination reaction, it converts into alkene and water eliminates. That is possible. It is not an oxidation reaction. Okay, so 1 degree alcohol gives you aldehyde. And on a strong oxidation, it gives acid. 2 degree alcohol, whether it is mild or strong, it converts into ketone. Done?
So could you repeat what you're saying? Your voice is breaking for me.
I said 1 degree alcohol gives you aldehyde or acid. You will get aldehyde when the oxidizing agent is weak or mild oxidizing agent, not very strong. But with a strong oxidizing agent, you get aldehyde first and that get oxidized into acid. So eventually you'll get acid, not aldehyde. Okay, you won't get mixture over here, right? You'll get acid. 2 degree alcohol gives you ketone, whatever the oxidizing agent. 3 degree gives you no oxidation. Okay, so this 2-3 things, on the basis of this, you can write down the product easily. Just you need to know whether the oxidizing agent is weak or strong. Okay, mild or strong. Correct. So we have only 3 strong oxidizing agents. Write down the oxidizing agent. Let's see this oxidizing agent, and this part you need to memorize. Okay. Okay. Correct. The first one, you see, we have acidified KMnO4, H plus KMnO4. The second one is acidified K2Cr2O7, and the third one is chromic oxide CrO3 with H2SO4. All these are strong oxidizing agent. Oh, I forgot to write. Here write down a strong oxidizing agent on the top. Okay, all these are strong oxidizing agents. Okay, so with this, you just need to know the conversion of 1 degree into what and 2 degree into what. Okay, now when you use this, it's one information I'm giving you here, not very important. KMnO4 is in +7 oxidation state, and it converts into MnO2 in this reaction with alcohol, right? So this is of purple color, and this converts into brown. This is the color change we have. K2Cr2O7, again it is in +6 oxidation state, and it converts into Cr+3. This is orange, and this is green, right? This too is the test of, again, alcohol, 1 degree or 2 degree alcohol. Test of 1 degree and 2 degree alcohol. Okay. Now, so only 3 we have: strong oxidizing agent. Mild oxidizing agent are the first one is red hot copper. Red hot copper, that is copper we use at around 300 degrees Celsius. Okay, so when you have 1 degree alcohols, for example, CS3CH2 OH with this reagent, red hot copper, it converts into aldehyde with equal number of carbon atoms. Okay, OH with this 2 degree double bond O. Copy this down. Okay, 1 degree gives you aldehyde, 2 degree gives you ketone. The second one, the mild oxidizing agent, is NBS.
Can you go back to the previous slide just for 1 second?
Yeah.
Yes, sir, done.
Just a second. Yeah. Next one is NBS. So we have RCH2OH. With NBS, it converts into, again, RCHO aldehyde, and with ketone, 2 degree alcohol, it converts into ketone. Nothing much you have to do. The third one, this one is important, PCC. It is pyridinum chlorochromate. Pyridinum
So what was NBS again?
and bromosuccinamide. Pyridinum chlorochromate. So it is pyridine, the mixture of pyridine with HCl plus CrO3. This is PCC. But you have to keep this thing in mind, PCC. In the question also, you'll get PCC written. Next one is PDC. PDC.
So these are all mild, right?
All mild. This is pyridinum dichromate. PDC, pyridinum dichromate. Pyridinum dichromate is this. Positive charge, hold twice, Cr2O7. Okay. Next one. The fifth one is Sarret's reagent. Sarret's reagent. We have the mixture of pyridine plus chromic oxide plus HCl and CH2Cl2. Means in PCC, if you add dichloromethane, you'll get this. Next one is Collins reagent. Collins reagent is this. We take 2 moles of pyridine in this with chromic oxide and CH2Cl2. This one. The most important one, yes.
So what's the point of adding CH2Cl2? Both
See,
are
nothing
mild.
like, see, any oxidizing agent, any reaction, oxidation of any compound, you can have different reagent possible. Correct. So it is possible with this mixture also and with this mixture also. Dichloromethane is what? It is a non-polar solvent. Right? CCl4 is a non-polar solvent. It is a polar solvent, right? CCl4 is non-polar. This one is polar. So basically we are increasing the polarity. Maybe it is possible with this one, the reaction can take place easier. Right.
So, could you go to the previous page? Just 1 second. I couldn't write everything else. So, and all of these are the weak oxidizing agents, right?
All these are weak, you can say, mild, you can say, not strong.
So like these ones can't make a carboxylic acid?
No.
Okay. So do we need to remember the structure?
No, you just need to know this. PCC is a weak oxidizing agent, mild. PDC is a mild oxidizing.
Okay.
Okay. Better is what? You just memorize those 3 are the strong one. KMNO4, K2Cr2O7 in acidic medium, and CrO3 in again acidic medium, H2SO4. The rest of them are mild oxidizing agent. MnO2, manganese dioxide. It is also very important. Okay, write down, it oxidizes only allylic and benzylic alcohol. It oxidizes only allylic or benzylic alcohol. Okay. This reaction you see, CH2 double
Why
bond.
does it only oxidize allylic or benzylic alcohols?
See, mechanism for this you need to see, then you can understand this. Okay. Mechanism I can show you. Okay, I'll show you the mechanism later in the next class. Okay. But mechanism usually, I don't teach because like I said, for all these reagents, you just need to know how to write down the product.
Okay, sir.
But reason why it oxidizes allylic, that you can understand by the reagent that forms. Maybe, the reagent that forms at allylic and benzylic position, that may be stable. Hence, it is possible. So if you want, I can give you the explanation next class. I'll give you that. Okay. So for today, you just write it down, the reaction, because in the exam also, they will, you are not going to write down the mechanism. This one is 1 degree. You see, it is at allylic position, correct? With MnO2, it oxidizes this, since it is 1 degree alcohol, so it converts into what? Aldehyde. That is it. And that's why I don't teach mechanism for all this, because eventually you have to memorize this only. But yes, I'll explain that next class. No worry. Okay, you have a benzaldehyde, that is CH2OH here. Sorry, benzyl alcohol it is. With MnO2, we get here what? Benzaldehyde, CHO. It's very important. Okay, on this they have asked question in the exam. Benzaldehyde. 2 degree alcohol, if you use at allylic position, for example, copy this down, I'll show you. Finish. Okay. CH2 double bond, CH single bond, CHOH, CH3 with MnO2. So wherever you see allylic or benzylic alcohol, you just the preferred reagent is MnO2. Okay, C double bond O and CH3. Look at this question. OH with PCC and with MnO2. What is the product we get?
So both separately, right?
Yes, separately. So MnO2 can oxidize only allylic or benzylic. It won't oxidize anything else.
So does MnO2 oxidize allylic or benzylic only because of the resonance formed?
I have to see the mechanism for that. Okay, basically, I mean, like I said, when you look at the mechanism, you can probably understand that probably here the intermediate that is forming, that may be stable intermediate forming because of resonance, because of allylic position we have resonance possible, no benzylic position we have resonance possible. That is the possible reason, but exact mechanism I don't remember now. Okay, so I can tell you in the next class, but that could be the possible reason. That's why it is allylic and benzylic.
Yes.
Okay, so PCC, what it does, it won't oxidize this allylic form, right? So the product here would be, this will be as it is. Okay, and this gives you, one more we have here, no, 1, 2, 3. So 1, 2, 3. This would be 2 degrees, so double bond O. And here we get this one, 1 degree. So we have double bond O and H aldehyde. Correct? PCC. But when we have MnO2, so this part will be as it is. And since it is 2 degree alcohol here, it converts into a ketone. OH as it is. And here we have OH.
So can a strong oxidizing agent oxidize allylic or benzylic position?
No, it's not. It's not. Because this question they ask in the exam also. That what is the, like this only they have asked many questions in NEET and JEE Mains. That which of this oxidizing agent we use to oxidize this alcohol, and the structure they will give it, they'll give you this allylic alcohol or benzylic alcohol, and then 1 degree, 2 degree, like that it will be given. In that one, we do not opt the strong oxidizing agent. Okay, we take only MnO2. Okay, so that we don't consider.
Yes, sir.
Yeah. Done. Okay, the next reagent we use 3 different compounds into this. Okay, it's not complex. I'll discuss the mechanism for this one. Okay, it's not complex, but yes, in the reaction it will be given stepwise manner. Okay, so next one, I forgot the number. What number was this? You just write it down. The reagent we use in the order. The first one we use TSCl, and why we use TSCl?
So to get good
living group. That is the only purpose, to convert a poor living group into a good living group. And then we have NaHCO3. There's 3 different reagents we use. Okay, suppose we have 1 degree alcohol. For example, we have R. Yes.
This comes under which category?
It is the next oxidation, mild only oxidizing agent.
Okay.
All these are mild. Like I said, we have only 3 strong oxidizing agents. Okay, so we have 1 degree alcohol, 1 degree alcohol when reacts with this, what it forms? Could you tell me? OTS, yes or no? With TSCl. HCl will go out, correct? No. You see, OH converts into what? A good leaving group, that is OTS. And that is what the purpose of this. Now what happens? Next we are using dimethyl sulfoxide. Dimethyl sulfoxide, if you look at the structure, it is O double bond S CH3 CH3. This is what kind of solvent it is? Polar aprotic, right? This attacks onto this carbon atom, the lone pair of oxygen, and this leaving group goes out. So what happens here, you see, we have RCHO. I'm writing it down in one single step, CH3 CH3, plus we get OTS minus. Okay, this one you see, we have hydrogen present. I can also write this comes over here. Here we have the positive charge, and this attacks onto this. We'll get this. Yes or no? Correct. Now in the next step we are using NaHCO3. NaHCO3. Now NaHCO3, what it does, it takes this H plus, and this bond comes over here, and this goes out again as a leaving group. Thioether forms. And the product is what? The product is R C double bond OH plus thioether, and this H is taken up by this, it forms TSOH. This is the product you get.
So are the byproducts important?
No, not important. You just need to know that 1 degree converts into aldehyde. That is it. Mechanism also, I'm telling you, it is not important, not at all important for this one. Wherever if it is important, I tell you always that here you have to keep the mechanism in mind. This part is important. For this oxidation thing, right, oxidation reduction reaction mechanism is not at all important. Yeah, I'm coming to that, Varun. That's nice. That's a good question. The question is, what is the role of this NaHCO3? See, there is a reason why we have this organic chemistry in 12th standard. Okay, why we are not studying all these in 11th standard? So there must be some reason for this. If you actually want to understand the mechanism, we somewhere at some point we use the concept of physical chemistry that we have studied before. Like in this case, it's the ideal example for that. I can make you understand what I'm saying now. You see, this NaHCO3 is what? Could you tell me what is NaHCO3? What is NaHCO3? How do we get NaHCO3? Could you tell me the reaction? Anyone?
H2CO3
H2CO3
plus NaOH.
So what is this? NaOH and H2CO3? Tell me. It is a strong base.
Acid.
Strong base, weak acid.
Weak acid, correct? So what we can say, it is a salt of what?
Strong base and weak.
Strong base and weak acid. So its aqueous solution would be what? Its solution would be what? Basic in nature, because we have weak, we have strong base. Salt hydrolysis kiya hai na? Salt hydrolysis, and we have discussed all this that weak acid plus a strong base gives basic solution. Strong acid plus weak base gives acidic solution, right? So NaHCO3 that we are using here, actually this solution is basic, and hence it extracts this H plus formulas and the reaction process. Did you get it now, Varun?
So, but it's just a mild base, right?
Yeah, that's
it's only
what.
mild.
You can take any basic thing over here. You can take any basic thing over here, right? If you take very strong base here, right, then it probably can affect, yeah, with HCl also. That's why and now this thing is very experimental actually. When you do this in the lab, then that's why in the book the thing that is given, it is ideal. Like they can take, suppose basic solution ही लेना है, NaOH ले लेते. Are you getting it? Why we are not taking NaOH? Because NaOH फिर HCl से भी maybe probably it can react. Okay, unneutralized हो जाएगा solution. Correct. So we are not taking NaOH. For that, we could have different reasons. Okay. That's why you should keep this in mind. We won't take, ideally, we won't take a strong base, but we can take salt of any strong base and weak acid for this purpose. Right. Now, this thing you can understand once you know the concept of salt hydrolysis, ionic equilibrium and all. Correct. That's why we are doing all these things in 12 case. So understood, guys, why we have used this NaHCO3 here? No doubt.
Yes, so
So
good.
this thing, this thing actually in JEE Advanced, they can change these reagents over here because this requires a very depth concept requires for this. Okay. Or they can ask you questions based on this part. Okay. Usually we suppose if you simply mug up these three and you are not getting NaHCO3 here. If you do not know this logic, then probably you won't be able to get it. Right. This is whether this kind of understanding is required for JEE Advanced. For mains and all these things, they won't ask at all. Okay, so this is the reaction from which overall kya ho raha hai? Overall we are getting aldehyde from alcohol. That is it. What are the reagents we are using? We are using THCl, DMSO, and a salt of strong base and weak acid. Okay. Quickly, we'll finish two more reaction here because if I finish only one, okay, then the other one is exactly related to the previous one, this one that I'm going to do now. Okay, so we'll do two more reactions. We have 10 minutes. I think I can finish this. So the next oxidation is opener oxidation. It is important. It is a name reaction. We call it as OPPENAUR, opener oxidation. You have to memorize the reagent that we are using here. The reagent for this, we are using ALO whole thrice. It is tertiary butoxide actually, whole thrice. And the solvent is acetone. Right? The name of this compound is aluminium tri tertiary butoxide tertiary butoxide. Okay, this compound is this with acetone. Okay, now this compound I'll write down here. This compound dissociates and it forms Al3 plus 3 of this ion, actually, O minus. Okay, now this reacts with alcohol, right? Suppose I'm taking 2-degree alcohol here, OH. We have O minus and 3 moles of this. Since we have 3 moles of this, so we'll take 3 moles of alcohol also. Now this reaction is what? This reaction is acid-base reaction. What happens in this reaction? You see, this is base and this is acid because we have acidic hydrogen present here. It takes H plus from Mehul, you just disconnect and rejoin. Okay, I can't see if you do not see the next slide. Some network problem from all of you can see the screen?
Yes, sir.
Right, so disconnect, yeah, okay. So this is acid, this is base. It takes this H plus and it forms this compound. We have O minus and alcohol. 3 moles. Now here we have the role of acetone. So what happens here in the next step? We have one hydrogen present here, and this is now the hydride ion donor, right? And the acetone, we have 3 moles of this. For complete reaction, we'll take 3 moles of acetone also. This electron pair comes down, and this goes out as hydride ion, and this attacks onto this carbon atom. This goes up, right? And hence the compound that we get, 3 moles of this ketone and 3 moles of this ion. So this get reduced. except hydrides ion, this get reduced and we convert into ketone. This one is this, right? One more important thing here, we are using this tertiary tributoxide ion here, and that is what we are getting with respect to this only, we are getting the alcohol. So they may ask you, what is the alcohol we get in this reaction? Okay, so with respect to this, we'll get this alcohol. Okay, and since you see 3 moles of this we have, so this will get neutralized by this. These two combines with aluminium and it forms O tries, like this it forms finally. Not important, the product is this. Opener oxidation. Finish. Okay. So basically you need to know the reagent, and the thing is again same. 2-degree alcohol converts into ketone. This oxidation is mainly for ketone only, like conversion into ketone. So mainly we use this for 2-degree alcohol, and we get ketone from 2-degree alcohol. That is the basic thing that we have already discussed. So opener oxidation, it is a name reaction. It converts 2-degree alcohol into ketone, and that is what you have to memorize with this reagent. Mechanism is again not important here. Now the next reaction is it is exactly opposite to
So does that work for primary alcohol as well?
No, like it is a name reaction, so it is defined for what molecule we are using it.
Okay.
It is used for all the name reactions is defined, whether it is for aldehyde or ketone or any other compound. Okay, like if I talk about Baeyer-Villiger oxidation reaction, it is given for this thing ketone, but it is applicable for both aldehyde and ketone both. It is mentioned. So here it is mainly for ketone, opener oxidation.
Yes.
Okay. Now the next reaction is the exactly opposite of opener oxidation. It is a reduction reaction, but since it is exactly opposite of opener oxidation, hence I am doing it here only. And this, the name of the reaction is MPV reduction reaction. Write down, it is exactly opposite of opener oxidation. MPV reduction reaction. This MPV stands for Mervin-Pondorf Pondorf Worley, Verley. Mervin-Pondorf-Worley reaction. You'll get as MPV only. Okay. In this, what happens? It is exactly opposite of opener. So ketone converts into what?
2-degree alcohol.
Ketone converts into 2-degree alcohol. And what is the reagent we use? We use ALO. We have hydrogen here, right? And the solvent is the conjugate acid of this compound, which is this one. It is a conjugate acid of this. Okay. Again, what happens? This dissociates like Al3 plus and 3 molecules of this. Correct? Now, this molecule reacts with ketone. So suppose I am taking this ketone, that is the reactant, and the reagent is this. We have O minus, correct? So I'll write down this way. O minus, exactly opposite. We have hydrogen here. So when this lone pair of electron forms a pi bond here, this hydride ion comes out, attacks onto this carbon, and this pi electron goes onto this oxygen atom. So this is reduction of this, and this get oxidized. So this converts into what? It converts into ketone, plus this converts into this one, which is O minus here, and the hydrogen present over here. Okay, now this O minus get protonates by the solvent in the next step. So you have O minus with the solvent HO, this, it comes over here, protonation takes place, and hence it converts into 2-degree alcohol, plus we get the conjugate base of this acid. And this one, obviously we have 3 moles of everything. Okay, I'll write down here. Because we have 3 moles of this. So this is 3 mole, this is 3 mole, this is 3 mole, this is 3 mole. 3 mole of this we use here, 3 moles of this, 3 moles of this, and 3 moles of this. So this and Al3 plus combines and it forms Al O whole thrice. This is the reaction we have. It's there only. It's, I do not write it here, but it is understood. No, it is a bond line is structured through. So it is here only. Okay.
So did we get back the same reagent we used, sir, in the last?
What?
So we got that Al compound, right? Isn't that the same thing as what we got as a reagent?
Reagent, yeah, we get the same thing. No, so the concentration of this won't change in the reaction.
Okay, sir.
That's what it means. The concentration won't change. Okay, so this is it. We have done done so many.
So you told us exact opposite. Shouldn't we get third butoxide?
Sorry, what? No.
You
See,
told
no, opposite in the sense we are getting ketone from alcohol. No, it is
yes.
alcohol from ketone. And similar reagent, exactly similar reagent we do not have, but see, we are getting here acetone, there the acetone we are using as a solvent. I think there we are getting alcohol, no, as one of the product.
Yes.
Right, there we are getting alcohol, and here we are using this alcohol as a solvent. In that sense it is. Okay.
Yeah.
So again, you see the mechanism, you don't have to memorize here. Direct, you will get the answer. Okay, the only thing you should know that one thing was there, we have this solvent. One thing is what, that this alcohol, they haven't asked this thing yet, but since mechanism we have discussed, one thing you see, this H is coming from the solvent, right? So if you take here deuterium, then the answer on this you'll get here deuterium. You see, this comes over here. This kind of thing you should keep in mind once we discuss mechanism. And these possibilities are not there in all those oxidation reactions. That's why the reaction mechanism is not important over there. Here also, they haven't done this, asked this kind of question. But if you want, you can keep that in mind. Okay. So guys, we have done alkyne oxidation reaction. We have done oxidation of alcohol. Okay. Next, we have to start with the next class, oxidation of aldehyde and ketone. Okay, and then we'll start with reduction reaction. Okay, the last part of this chapter. Okay, so I'll share the PDF. 2 PDFs are there. Obviously, all the questions you cannot do now because we haven't finished it yet. But obviously, whatever you can, reactions of Grignard reagent you can try, and alcohol alkene you can try. Okay. Anything else?
Thank you, sir.
Okay. Thank you, guys. Take care.
Thank
Bye.
you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Yes, sir.